Question 5 says, when a wire carries a current of 1.20 amperes, the drift velocity, the average velocity with which the electrons float along the wire is 1.20 times 10 to the minus 4 meter per second. What is the drift velocity when the current is 6 ampere? Okay, so the question is, basically there are two different conditions. Initially, what you have is a current that is equal to 1.20 ampere, and drift velocity, I'm going to write it as V sub d, is given to you as 1.20 times 10 to the minus 4 meter per second. Okay, and afterwards what we have is this current now is 6.00 amperes, and we need to find the drift velocity. Okay, so we're going to use the formula I current is equal to number density, that is number of these charges per unit volume, times the charge on one single particle, times the drift velocity, times the area, the cross-sectional area. So if you want to talk more about this, I would say this like let's say a wire like this, and its cross-sectional area is A, and there's like these electrons in it, has some density small n, and they're traveling. That constitutes a current, and that current is given in terms of the velocity of these electrons, cross-sectional area, and charge on these electrons, and density, the number density of these electrons or these charges. So I'm going to use the formula I equals NQVDA. Okay, now this means that I is going to be, I'm just going to substitute these values. It's going to be N is not given to us, Q is not given to us technically, and let's write down A in front of VD. Okay, and I'm going to use VD as 1.20 times 10 to the minus 4. I divide both sides by 1.20 times 10 to the minus 4, and I end up with 10 to the 4 equals NQA. That is my equation 1. Now, important thing to remember here is, it doesn't say in the problem that the number density is different in a later case. That means the number density is same, and also that means is the and it's a safe guess, and it is also not given the problem. So it is what it is, and that is that the area, the cross-sectional area, is not changing. Okay, so that means N small q, small n, small q, and capital A are not changing. That means this quantity NQA is equal to 10 to the 4. Now let's look at the case when the current is and then the current is 6.00 amperes. So I'm going to use the same formula, I equals NQVDA, and let's do this. I is 6.0 ampere, and I'm going to write NQ and A closely, and then VD here, NQA and VD. For this case, oh well, VD is what we need to find. Okay, alright, no problem. A is equal to 6.0. Let's divide both sides by NQ and A. So we'll end up with 6 over NQA equals VD. And I'm going to use equation number 1 here, and I'm going to substitute that in here. So I get VD equals 6 divided by 10 to the 4, and this gives me VD equals 6 times 10 to the minus 4. You can go ahead and write this as meter per second because you have already written down everything in SI. So this should also be in SI, and that's what we get as an answer. 6 times 10 to the minus 4 meter per second. Question 6. Question 6 says that this is a circuit given to you, okay? And there are 1, 2, 3 resistors here, and we need to find the voltage across the 10 ohm resistor. Okay, so the idea is, okay, let me first make this more boxy so that it becomes more familiar to to what we have already seen. So far we have only seen that circuits were a little more boxy, right? And this is a good place to remind us all that these horizontal and vertical lines that you see are wires, so you can twist them, bend them, make 90-degree turn. Those kind of things can be done. And also a lot of times you'd see we're familiar with this as the sign of a battery, and this is positive and this is negative terminal. This is same as having this is also a battery, and you can have as much as you want. This is also a battery. Just make sure, which I didn't here, that you end up with the big bar. You start with big bar and then you end with this small bar. So because you start with positive and then you end up with negative, for example. Alright, so this is the same thing. So I'm just gonna make this battery sign more like what we have already seen. This is 20 volts, 2 ohms, 5 ohms, and then 10 ohms. So the question is, we need to find the voltage drop across the 10 ohms resistor. Okay, so if you have already seen Kirchhoff rules, so you should know that the convention says, I'm just going to remind you all, the convention says that if you have resistance like this, and then this is the current, and you're moving in like this, so that means you're traveling with the current. That means the potential drop is, if this is A, this is B, del V is B minus A, is I know this is too small to understand. So I'm just gonna, oops, no. Okay. All right. Not a good idea. Oops. No. All right. Let's see. So this is what's happening here. Sun convention, right? This is what I'm saying. Resistor like this, if the current is in this direction or you're moving from left to right, this is B, this is A, VB minus VA, delta V is given, if you're moving in the direction, is minus IR. If you're moving opposite to the direction of the current, delta V equals to plus IR. If you're moving like this and then the battery is like this, then delta V equals to minus V or epsilon. We have already seen this, and if it's opposite, it's plus V. So if you have not already seen this, go ahead, revisit the previous video or see your recitation, and then maybe in your notebook you have these conventions there. So that's what I'm going to use. I'm going to use Kirchhoff laws and these conventions here. So I'm just going to make this more clean now. Right. So this is the circuit we have got, right? So let me just go ahead and make few currents here. So I'm going to say that in this branch we have current I1 coming in, this we have current I2 going out, and here we have got current I3 going out like this. Okay, so the very first thing you should do is write down the equation at this node right here, and that is I1 equals to I2 plus I3, conservation of current, or junction law or junction rule that you're more familiar with. So that's what it is. I'm going to name this equation equation 1. Now I do this. I say in here I'm gonna be going like this in the clockwise direction. Here also I'm gonna go in a clockwise direction. This is a sense of rotation of the how I will be picking up each element in this loop. So you guys have already seen me do it. You guys have already seen this in your recitation and lectures. So that's what I'm doing. I'm writing. I'm choosing the direction to follow, that I will be following in this problem, to use the second rule of Kirchhoff's. Okay, so let's name these nodes. It's easier that way, but you don't have to. C, D, E, F. Okay, so let's start with the loop A, B, C, F, A. So in loop A, B, C, F, A, I start at point A. The very first thing I see is this battery right here. Okay, so this is what I'm going. I'm doing like this. This is how I'm going. I'm going to make a full circle. So the very first thing I see is the battery, and here you can see that the current I3 is in this direction. That means going through the battery like this. That means the sense of the rotation is same as the direction of the current, and if that happens in the case of battery, I write down the opposite sign of the incoming direction. That means that we are coming in from here. This is negative, this is positive, so I'm going to write down positive 20 volts. Next thing I see is this resistor. Okay, so in this I'm traveling with the direction of the current, because we have got this I1 current in this branch, and with the direction of the current you write this as minus whatever current is times the resistance. Now I go to point F, and then from F to A I've got another resistor here, 2 ohms, and here again the direction of the current is same as the direction of the rotation, so I'm just going to write it as I3 minus I3 times 2 equals to 0. That is equation number 2. Okay, you do this with another loop and you get, let's say we take F, C, D, E, F. Okay, and from F to C, well, here this is how you're rotating, and the current on this is I1 like that, so you're going in the direction opposite to the current. That means you'll have to do plus the current times the resistance. Now after crossing this, you go to 10 ohm resistor, and that means here the direction of the current is I2, which is like this. That means it's going to be opposite to the direction of the current. That means again you take plus I2 times 10, and that will be equal to 0, because you start at F, you end at F. The only two things that you see in the loop is one resistor of 5 ohms and the other resistor of 10 ohms. So you've got this as equation number 3. Now you can take another loop like this, the bigger one, but it's not necessary here. The reason it's not necessary here is you have 3 equations and you've got 3 unknowns. It's perfectly fine at this point to solve for these 3 unknowns, which are I1, I2 and I3. And just want to recall this, that in order to figure out the potential across 10 ohms, we really need to know what is the current here. So once we know the current, we just multiply by the resistance to get the potential difference. So that's why we are trying to find the current through this 10 ohm resistor. Okay, so having said that, yeah, forget about it. So yeah, that's what we need. If we know the current through the resistor 10 ohms, then we can know the potential difference. We just multiply the current by the resistance to get the potential difference. Now we have got 3 equations and 3 unknowns. We know how to do it. You substitute one equation into other, and then you just do equation gymnastics, and then you get the answer. So I'm going to do that for you. So I see that this equation is in terms of I1 and I3. This equation is in terms of I1 and I2. So if there was a way I could turn this equation 2 in terms of I1 and I2, then I can like maybe multiply something and subtract or add that to equation 3. I can get rid of one of the two between I1 and I2. So that's what exactly I'm going to do. I'm going to use I3 equals I1 minus I2 from equation number 1 minus I2. I'm going to use that in equation 2. So I'm going to end up with 20 minus I15 minus I1 minus I2 times 2 equals to 0, or 20 minus 5I1 minus 2I1 plus 2I2 equals to 0, and this is just 7I1 minus 7I1, and let's call this equation number 4. Just want to make sure that everything's correct here. I1 equals to I2 plus I3, that is correct. You go in loop ABCFA, you go in the direction of the current is in the direction of travel, so you write that as plus 20. Then I1 is in the direction of the travel, so that's minus I1, and same with minus I3 times the resistance. So equation 2 is correct. Equation 3, FCDEF, you start at F, the first resistor you see is 5 ohms, you're traveling in the opposite direction of the current, so you write it as plus I15, and then again 10 ohm resistor has current I2 in the opposite direction of the travel, so you write it as plus I210. From equation 1 you get I3 equals to I1 minus I2. You substitute that value in equation number 2, so you get 20 minus I1 times 5 minus I1 minus I2 times 2. You open the bracket, you multiply 2 by I1, so you get 2I1, you get minus 2I1, that will be added to 5I1 of negative, so you get minus 7I1, and then yeah, so the equation is correct. Equations are correct. So we've got equation 3 and equation 4 in terms of I1 and I2. Okay, so if I want to, okay, so this is what I'm going to do. I'm going to multiply equation 4 by 5, so I'm going to end up with 100 here, and then 35I1, and then 10I2 equals to 0. Let's call this equation number 5. So I have multiplied equation number 4 both sides by 5. Alright, so now I'm gonna subtract 5, equation number 5. I'm gonna subtract equation number 3 from 5. So I'll have 100. Make sure you're following this. 100 minus 35I1 plus 10I2 minus 5I1 minus 10I2 equals to 0. So let's call this equation number 6. So what I've done is just subtracted third, equation number 3 from equation number 5. You do, and it's your job to match these equations. So I get 100 minus 40I1 equals to 0. Nice. So I get I1 equals to 100 over 40, and that is equal to 5 over 2 amperes. That is I1. Nice. So now I have value of I1, and I can use this value in equation 3, this one, and this says that I1 times 5, so I'm going to use I1 equals to 5 over 2 times I1 plus I2 times 10 equals to 0. This implies that, alright, how do I do it? 5 over 2 is I1, and then that is multiplied by 5. This implies that I2 equals to, alright, I'm gonna do something here. I hope you guys are comfortable, but make sure that this works out. Just want to see if this is correct. This is correct, and then just use your calculator if you want. It's going to be minus 5 over 4 amperes. That's what I2 is, and that's what I needed. Okay, so I'm just going to do the remainder of the problem right here. I hope you guys follow this. So what's happening is I2 is this way, okay, and I want to figure out the potential difference across the 10 ohm resistor. So let's say we're figuring out VD minus VE. Okay, so if you're figuring out VD minus VE, and you know what, this will make more sense if we do VE minus VD, because here the sense of direction that we took originally was like this, right? And then VE minus VD, and then sense of direction and the direction of the current is opposite, so that means it's going to be plus I2 times R, that is just I2 times 10 ohms, and using the value I2 equals to minus 5 by 4, I write this as VE minus VD equals to minus 5 over 4 times 10, and that means we get minus 25 over 2, and then that should be minus, sorry about this, but I hope you guys are following. This is going to be minus 12.5 volts. Yeah, let's see. Alright, 12.5 is the answer. So yeah, you need equations, and then make sure the number of unknowns are at least same as number of equations you have. Substitute and then do the gymnastics to figure out the potential difference. Question 7. Figure 27.4 shows one branch of a large circuit. Find the current electric potential difference between point A and B, VA minus VB. So this should be easier because we have already done a problem like this, okay? But this is like very tiny part of it. So it says VA minus VB. So VA minus VB, okay? And let's say, I mean, this is entirely up to you, okay? So let's say you're traveling in this direction. This is the direction of travel. Let me choose another color. Mixture of red and black, I guess. So this is the direction of travel. Okay, so you start at B, and what do you see? So there are two things you need to consider. The direction of the travel. This is how we have developed the sign convention. What we have seen in the book, and what I have taught you in the recitation, what you've seen in the lectures, that can be different from your own convention. But the point is that you have to follow one convention and one only. Do not mix up convention in a single problem. So if you're solving a single problem, always follow the same convention, or you're going to end up with something that will not be the correct answer. Anyway, so VA minus VB, we start at point B. We are traveling in the direction of the current. Remember, this is the current direction. Okay, so this is the direction of the current. This is the direction of the travel. We're traveling in the direction of the current. We see a battery. The nearest terminal is positive. To write this as minus 10 volts. That's what our convention tells us. Then there's a resistor, and the current is going in the direction of the travel. So you write this as minus 10 times current I, which we know is 2 amperes. We're going to use that in a minute. And then you see another battery, this one. And here the nearest terminal is negative, and you are traveling in the direction of the current. That means what you're going to use here is positive 20 volts, and this means that it's just going to be minus 10 times 2 plus 20, and that should be minus 10 volts. VA minus VB. And we have answer to be plus 10 volts. That means that okay, yeah, should be, oh no, yeah. Right, so I made a mistake. VA minus VB should be positive because it's all right, so using the convention, like okay, so in the option that you should have, it would not be the case that plus 10 and minus 10 are given in the problem, because both are acceptable answer here. So what I'm trying to say is, look, VA minus VB, right? And we have got VA minus VB. The current is flowing from B to A. That means the higher potential is the point of B. The point B is at higher potential. That's why current is flowing from that direction to point A. That means that when you do VA minus VB that we have done, we should get the answer to be minus 10 volts instead of plus 10 volts. So if you're getting minus 10 volts, then you definitely, in the answer, you will definitely see either plus 10 volts or minus 10 volts and not anything else, and neither both of them. So the question will not be designed to check if your convention is the way the convention is followed by the person who has set up the question. Okay, and here for our problem, definitely it makes sense that VA minus VB is negative, because if the current is flowing from B to A, that means A is in a lower potential than B. So hence VA minus VB must be negative.